In the name of the Almighty God, I hope you're all doing great and in the best of spirit and health. In this video, we're going to be talking about Heap Sort, okay? Which is one of the most popular sorting algorithms. Since we know that there are a ton of different 30 plus, a ton of different sorting algorithms, but in this video, we're going to be doubling down on Heap Sort. But before we get to that, let's just a short, quick intro. What are sorting algorithms? We know that sorting algorithms or array sorting algorithms, since they mostly apply to arrays, but not only, you can also use them for other data structures, but mostly for arrays. So these sorting algorithms, they're a set of instructions or methods that are used to rearrange the elements in an array into a specific order, right? They used to rearrange the elements in an array into a specific order, typically numeral, alphabetical, ascending, descending. So that's sorting algorithms. They used to sort the data, put it in a specific order. So why is this important? This can be important for several reasons, for efficiency. Sorted data can be searched more efficiently. So this puts the data in a specific order. That makes it, easy to find a piece of data, easy to analyze it, and for patterns and trends and all. Okay, so it makes data easier to process, search, display. So a simple example could be like if we have an array that has random numbers, right? So we want to search a specific number, a specific element in a sense. So if it's out random, if it's not sorted, so we must use linear search, right? So go through every element one by one, and that's going to be really inefficient. But if it's sorted, then we can use binary search. That's going to be really more efficient. It's going to split the array, based on two parts, into two parts based on our input. One part that's smaller, one part that's bigger. Then it's just gonna constantly keep splitting the array and then just searching in the relevant part. So that's very efficient, right? So all in all, sorting algorithms are used to sort. It's that simple. They're used to sort, put the items, elements in an array or other data structure in a specific order. So that makes it easier to process, to search, to display, and for many different reasons. There are some other algorithms that I said, like binary search, that they require sorted data. So if it's not sorted, they cannot work. So as we said, that there are a ton of different sorting algorithms, but they all share some common characteristics. So one is time complexity. So this is basically, simply put, this is the time that it takes, right? How much time does this sorting algorithm take? How fast is it? How good is its performance, right? How fast is it to sort? How fast is it in sorting? But more specifically, we can say that this measures, how the time to sort increases with the size of the array, right? You're not talking, how fast is it with 5-10 elements, right? That's good, but how the time, how the speed is affected as the size of the array increases, right? It gets to thousands and hundreds and thousands of elements, right? So that's time complexity. Okay, so simply, how much time does it take, right? Or how the time to sort increases as the input size increases. Then it's space complexity. So this measures the amount of extra memory that the algorithm reads. So let me explain this alongside in place. So an in-place algorithm, it sorts the array without using extra space for another array, right? So you give it an input array, it just sorts it in place, as the name says, right? It sorts it in place. It doesn't use any other array. So it just takes the array and swaps the element, goes through the elements, swaps them, puts them here, there. It doesn't use any additional memory. It just just uses the input array itself and then a couple of pointers or something, and then swaps the elements. So that's in place. So such algorithms that are in place, they have really great space complexity, right? They have a space complexity of, in a sense, O of 1. They don't use any extra memory, right? It's just the array itself. But then some other algorithms are not in place, like the divide and conquer algorithms. For example, the merge sort and other ones, right? Temp sort, merge sort, I guess these ones. They're divide and conquer. So you give them an input array, and then they just split it into two other arrays. And then they sort each array, and then merge them into another array. So these are not in place, right? Clearly, they're not in place. They're not satisfied with the input arrays, just take this array and swap the elements. No, we are more advanced elements. We split it and then we put it back together and all. So they're not in place, and they're gonna have a little worse space complexity, right? In terms of the amount of memory, right? They're gonna end up using more memory. But one more point in here, basically, this, generally speaking, there's a trade-off between time complexity and space complexity. Generally speaking, I'm saying, right? Those algorithms that are really fast, right? They have great time complexity, they are fast and speedy. They use more memory. Okay, just like Heap Sort, Quick Sort and Merge Sort that we said, right? They are not in place. They divide and conquer and some other methods, but they're fast, but they use more memory. But those that use really less memory, like bubble sort, insertion sort, selection sort, right? They're all in place. They don't use anything more beyond the input array itself. They're gonna take a little more time. Okay, so we're gonna get to Heap Sort. Heap Sort is also in place, and it has a great space complexity, but it's also good fast. It's like it just strikes the balance with everything. But generally speaking, we're saying those that are fast, they require more memory. Those that require less memory, they're going to be slower. And the usage depends based on application. If you want speed, then we're going to go for ones that have great time complexity, right? But if memory usage is critical, then we're going to opt for ones that have good space complexity. So finally, stability. So stable sort algorithm keeps elements with equal keys in the same relative order in the sorted array as they were in the input. So what does this mean? I guess I have to go to Word to explain it better. So this is the input array that I'm going to give to a sorting algorithm to sort it out, right? So a stable sorting algorithm. So in here, you can see that we have 3 elements that are just equal, right? They're just the same. They're just equal, and they have no problem. So let me add one more name in here to make it better. So we have 3 elements that are equal, right? So let's just give them a name to identify, right? Let's say this is Bob 2. The algorithm is just getting Bob. So it's just a way for us to identify the Bobs, the different Bobs, right? So if I give this to the sorting algorithm, if a sorting algorithm is stable, so it's gonna sort out the array. Okay, yeah, it's gonna return Alex, then it's gonna return the 3 Bobs and Bob and Bob, and then it's gonna be Dave and Zach, right? So it will sort the array just like any other array, right? So we're just gonna have alphabetical ascending sorting. So the main point is stability. If a sorting algorithm is stable, it keeps the equal elements in the same order as they were in the input array, right? So these Bobs, they're all equal. So they could be anywhere, actually. They could be here, there, right? Anywhere, no problem. But if it's stable, it will keep them in the same order as they were in the input array. So for example, Bob 2 were here. If Bob 1 was here, Bob 3 was there. They will be kept in the same order. So it will be something like this, right? Yeah. Bob 2, Bob 1, Bob 3, they're all Bobs. They will be in their correct place, Alex, then Dave, then Zach. But if it's stable, it will keep them in the same order as they had appeared in the input array, right? But if a sorting algorithm is not stable, then it will sort, it's no problem. It will sort, but the sorting will not be wrong. Yeah, the Bobs are in their right place, but then they will not be in the same order as they were in the input array, right? Again, input array, we first had Bob 2, then Bob 1, then Bob 3, but this here we have Bob 1, then Bob 3, then Bob 2, right? So that's stable and non-stable, right? So that's stable sorting algorithm, and this is going to be non-stable. Okay, a stable sorting algorithm keeps the equal elements in the same order as they were in the input, keeps them in the same order as they were in the input. But non-stable, basically it can botch the order and change it. So where is this important? This can be important in database in some places, right? So we know that mostly in database we have elements by ID, right? The elements have a specific ID. But in here, if let's say we have Bob and same name that's appearing again and again. So we're just fetching data from the database and we're sorting based on name, right? We're sorting based on first name. So if it's a stable sorting algorithm, it's going to sort all of these names and then it's going to keep all the Bobs in the same order, right? And this, if you just fetch IDs alongside the names too, right? Then all the Bobs will be kept in the same order as they were in the database. Basically the input, right? So the database entries will be the input to the sorting algorithm. So they're going to be kept in the same order. So it's going to be the Bob with the first ID and then the second, so if it's not stable, then it can mingle, right? We will have Bobs in their correct place, just like here. Then, but we might have the Bob with ID 2 first, and then the Bob with ID 3. So that's the point with stable and non-stable sorting algorithms. So since there are a ton of sorting algorithms, so as I said before too, in this time complexity, space complexity comparison, right? The choice depends based on the size of the array. If you want better time complexity versus space complexity, and also whether the data is mostly mostly sorted or completely random, right? There are some algorithms that do better, if it's somewhat sorted, or some that do better that it's outright random, right? So that was a little intro on sorting algorithms. So now let's get specifically to heap sort. So what is a heap sort? So heap sort is a popular and efficient comparison-based sorting algorithm that uses a binary heap data structure. Okay? Heap sort uses a binary heap to sort the array. It's particularly good for large data sets. It's great, in a sense. It's a pretty efficient sorting algorithm. It's great for large data sets because it has a good average and worst case time complexity of O and log of n, right? That's a good time complexity, generally speaking. We know that time complexity of pretty basic sorting algorithms like bubble sort, merge sort, selection sort, bubble insertion selection, they have a space complexity of O n squared. That's really inefficient for large data sets. But this one, it has a space complexity of O n log of n, and that's pretty good for large data sets. And more advanced algorithms will have like O log of n, and that's going to be best, right? Okay, and so to better understand heap sort, so we should first take a look at the binary heap, right? Since heap sort uses heap. But what is a heap? Heap is a type of binary tree. But then what is a tree, right? So we should first take a look at the tree data structure briefly, and just climb up the ladder. So first up, tree. What is a tree? So tree is a nonlinear data structure that represents a hierarchical relationship among elements called nodes, right? So this is a tree data structure. We're gonna have a root element, and then the root will have children, and all of these elements are called nodes, right? Each node can have 0 or more children, and a single node called the root serves as the topmost element. So this guy is the root, and these are its children, and they can have their own children. And so this node's parent is the root, this node's parent is 15, like that. So that's the tree data structure. It organizes data, we can say it stores data, right? Stores and structures data based on hierarchical relationship. So some more characteristics, basically. We talked about it. We have the root, which is the topmost element that does not have a parent. Basically, it's the star of the tree. Then edge. So this is the link between the root and between the parent and the child. That's you can put it. So leaf. Leaf is a node without children. So these are all leaves. Nodes, they do not have children, right? Then sibling, nodes that are from the same parent, right? These are all siblings because they're all children of the parent root, the parent 2. So an ancestor, basically, it's a node that precedes another node in the path from the root. Okay? Ancestor. So for 2's parent is 9. But if you want to talk about 2's ancestors, then it's 9 and then 2, right? The whole deal that comes before it. Then descendants is the opposite, right? A node that comes after another node in the path from the root. So basically we have this root. These are its children, right? So let's say 12 is its child, but then 1, 7, so they're all descendants, right? So 12 is the direct child, but then the whole deal that comes after it are its descendants, right? So if you're talking about the root, then the whole tree is basically descendant of the root, right? But you can see 12, then 172, so they are, direct children, but also descendants of 12, right? So I hope you've got the difference between direct child, direct parent, and then ancestor descendant. So 9 is a direct parent of 2, but this whole deal, 9, 2, and other ones, they are descendants, and 12 is the direct child of this 2. But then this whole deal that comes after it, 12, 12, 1, 7, 2, and whatever, if there were more, then they are going to be, the descendants. So that was a little intro about tree. Then we have binary tree. So what's a binary tree, right? So we can see in here, this is a tree, this is a node, it has 1, 2, 3, 4, 5 children, and this one has 3, this one has 1. So that's just, there's no specific rule, right? That's a simple general tree. But binary tree is a tree in which each node has at most 2 children. Okay? A node cannot have more than 2 children. At most 2. It's binary, right? Binary means 2, right? So it can have no child at all, 1 or 2, right? At most 2 children. So they're commonly referred to as left and right child, and it's a pretty fundamental concept in computer science. It's used in many different applications for efficient storage, retrieval. Binary tree is really important, right? So that's what we're talking about right now too. Heap sort uses binary heap, which is a binary tree. And this is a simple tree as we saw before too. Okay, so this has 3 children, this has 3, this has 2, 1, but this is a binary tree. A node can have at most 2 children, no more, 0, 1, or 2. So 2, 2, 2, and these are leaf nodes, just no children, right? So now we get to binary heap. I guess we have enough, background information, right? We're just basically touching the surface in here. There are lots and lots of more detail, but just to just wrap our head around the basics, right? So binary heap is a complete binary tree, which can be either a max heap or a min heap. Okay, so one thing I've missed in here is a complete binary tree. So this is a binary tree, right? So complete binary tree is a tree that has full nodes in each level, right? What I mean is that each and every node will have 2 children. That's full nodes, right? Full children. It will be full in each level, right? So in this level we can have 2, so it has 2. So this level each should have 2. Yeah, correct. So it can have full nodes in each level. It should have full nodes, full children in each level, bar the final level, right? Let me put it this way. It should have full nodes, full children, in each level, leaving the final level. In the final level, we have the leaf nodes, right? So they can have no children, but there's one more requirement. It should be filled from left to right. Okay, so this tree in here, this is not a complete binary tree. Why? But it has full nodes in level 1, okay. So if this is level 1, so I mean in level 2, then level 3. But in level 4, it's not, filled from left to right. This one is empty, and then this one has something, right? So this will not be a complete binary tree. So complete binary tree, it has full nodes in each level. Let me show you a heap. So heap is a complete binary tree, right? You can clearly see in here. Has full nodes in each level. In each level, all the all the nodes should have 2 children. 2 children, right? But then the final level, then it should not have any child at all, or if it has, 1 child or whatever, then it should be from left to right. So for example, if it had a child in here, then nothing, okay, that was complete binary tree. But if this had a child, then that would not be a complete binary tree. So it should be filled from left to right. Okay, so I hope that's clear with complete binary tree. In each level, we should have full children, just leaving the final level. And in the final level, it should be from left to right, right? In the final level, it should be from left to right, but in here we can have 2 or we can have 1, and then the other ones, or leaves, they don't have it, so that's no problem. And that's going to be a complete binary tree. Full nodes, full children in each level, and just leaving the final level, which can have leaf nodes. But if the final level also has some children, so it should be from left to right. Okay, so that's a complete binary tree. I hope it's clear. So it wasn't that important, but I guess to know the whole deal, but no problem. Okay, so let's continue with our binary heap. So binary heap is a complete binary tree, so I hope you've got the difference, right? It's a binary tree, but just with that additional point that it is a complete binary tree, which means that it will have full nodes in each level, just leaving the final level, that it may have 0, 1, or 2, but it should be from left to right. So it's a complete binary tree, which can be either a max heap or a min heap, right? So in a max heap, the parent node is always greater than or equal to its child nodes. Okay, in a max heap, the parent node is always greater, and in a min heap, the parent node is always smaller. So the heap can be represented as an array, where for any given node at index I, its children are at indices 2i plus 1 and 2i plus 2, and the parent. So we're gonna look at this in more example, and then that's gonna make more sense. We can read this if you want, right? But we're gonna explain them as we go. So this is a min heap, right? As we said, min heap. In the min heap, the parent is smaller than or equal to its children, right? So if every parent is smaller than or equal to children, every parent is smaller than the children, so generally speaking, then the root will be the smallest in the entire tree, in the entire heap. So that's a min heap, okay? The parent is smaller than its children. The parent smaller than children, this parent smaller than children, right? So that's a min heap. And if you have some information about BST or other things, that's different. In BST, the binary search tree, we have an element in here, then the left side of the tree are all elements that are smaller than it, the right side are all elements that are bigger than it, right? In here it's not like that, it's different. The heap property is basically it's min heap or max heap. In min heap, the parent is always smaller or equal to its children. So that will, if every parent is smaller than or equal to its children, then that will put the root element, as the smallest, the minimum element as the root, right? Then a max heap, it's the opposite. The parent is always bigger than or equal to its children. A parent bigger than its children, you can see the parent bigger than its children or equal to, no problem, okay? Bigger than or equal to its children. So if you have this property, then the root will end up being the maximum, the biggest element. So this is exactly what we are using in the heap sort, right? So if I just give you very short information, we will take an input array, right? Then we make a heap out of it, right? If we want ascending order, we will make a max heap, or if you want descending, we will make a min heap. So let's say we want ascending, we'll make a max heap, and that'll put the biggest element in the root. I mean, you got that, right? Max heap, the parent should be bigger than the children. So it's just going to go through the array and make a max heap out of it. Every parent bigger than children, every parent bigger than the children, and then that'll put the biggest element in the root. And then this biggest element will be extracted, taken out of this taken out of this heap, and then put as the final element of the array. That's it. Got it? That will be the final element of the sorted array. So the sorted array is made one element at a time. And then again we heapify, and then that'll put the next biggest element right here, and then that'll be put behind it, right? So that's how we can do ascending, descending order. So this was just a very short intro, and then we will get to it, no problem. So this is a array, right? This is an array, and then this is the tree representation of that array. So I'm just specifically talking about this point in here, right? So we can say the binary heap can be represented as an array, where for any given node at index I, its children are at indices 2i plus 1 and 2i plus 2, right? So basically we're talking about an index I, index 0. So its children, so basically we said that it's a complete binary tree. It should have two children or no children, right? So in the first levels, every and each parent will have two children, right? So for an index I, we're going to have the parent, and then in 2i plus 1, we can have its left child and then the right child. So, but if we have a child element, then the parent can be found at index I minus 1 divided by 2. So then We can talk about that in, I guess that's not needed to be explained now. We can just take a look at this array and this tree and then apply the formulas and all and see how does that work, right? So here we go. This is the array, and then this is the root. This is the first parent. So it has these two childs. This is index I, and then the first child is 2i plus 1. So 2, 0, that's going to be 1, right? 2 times 0 plus 1. So that's going to be 1. The second child is at 2i plus 2. That's 2 times 0. That's 0 plus 2 in here, right? So this is the the parent. These two are its children, and then this is another parent, right? And then these two will be its children, as we can see in here, right? 36, 25, 1. So it's first 100, 19, 36, as you can see in here. And then 19 has 17, 3. It will be after that. Then 36 has 25, 1, like that. And then 17 has 2, 7, like that, okay? So this is how we can represent the tree. So it's fairly understandable like this. Very simple, right? But this is how we can represent it, represent the tree as an array, right? So it's possible because it's a complete binary tree. So each node, in each level, we do have two child, right? So this has two children, and then this will be the two children of this guy, and then these will be the two children of this one, and then like that. So again, another example, you can clearly see complete binary tree, right? Full nodes in each level. Just the final level can can have less nodes, and it should be from left to right, right? You can clearly see it's like that. The left node has two children, and then the other one's not. But if this two children were in here, then that would not have been a complete binary tree, and this array representation would be nullified, right? Since in here, this comes here, and then the children come in that order, with that index and all, right? And in that case, it would not be correct. So we can just do the math and apply those formulas on this array and then this tree yourself and see how do they fit, right? So the main point is to know that we can represent the tree that we saw in these graphics and all as an array. And how? Like this, right? We have the parent and the children, then the parent, the parent, and then the children. Then so this is the parent, these are its children, this is the parent, these are its children. It's okay. So index I, then 2i plus 1, 2i plus 2, and then I minus 1 divided by 2, like that. So that's exactly what we are doing in here in the heap sort. So we take an array, we take an input array, random order, and then we turn it into a heap, like this. We turn it into a heap, and then this is the first element that we're going to extract. As I said, we're going to extract this, we're going to put it right at the end, and then we're just going to, so that's out of the flow, right? This 100 will go to the end, so this is max heap. It will be used for ascending order. So this will go right to the end, and then that's out of the flow now. We're just going to make a heap of these elements left, and then that'll again put the biggest element right here at the end, and then that'll be extracted, and then like that we're gonna end up with an array sorted in ascending order, right? That's basically heap sort, sorting with a binary heap, right? We create a binary heap out of the data, which will put the biggest or the smallest element at the root, and then that'll be extracted, one at a time, and then we're gonna have a sorted array at our hands. So characteristics of a heap sort. So efficient. We explained these things before now, right? Generally speaking, heap sort is a pretty efficient. It has good performance. The time complexity is good, O(n) log of n, and it's a pretty efficient algorithm. And then it's not stable. We talked about stability, right? So heap sort is not stable. It does not keep the relative order of equal elements, and they may be mingled up, right? But the sorting is in place, but the relative order of equal elements may change, and we talked about this, right? So heap sort is not stable. And then it's in place. Okay, so heap sort, we talked about what's in place and what's not. So heap sort sorts the array only with a constant amount of additional space, thereby ensuring low space complexity. So it has a low space complexity. So that's why it's efficient. In terms of space complexity, it's good, and in terms of performance and time complexity, it's also not bad. So generally speaking, it's, as I said, it strikes the balance. It's a great sorting algorithm. The space complexity is good, the time complexity is also good. So it's a pretty great sorting algorithm. and it's not stable, and it's also in place. Why it's in place? Since it takes an input array and then heapifies it, right? Just swaps the elements in place like this, creates a heap. Then move this to the left, move this element to the end, and then swaps these remaining one and moves one to the end, and then like that. So it doesn't need any additional memory for another array, right? It doesn't create any different array. It just takes the same array and then shows off all its skills on that. It doesn't split it or do anything else. So now that we have information, so basically I did say this before that heap sort, so basically it's a two-step process. First, we build the heap out of the data. So if you want ascending order, we're gonna build a max heap. If you want descending, we're gonna build a min heap. And then we repeatedly remove the root and then reheapify. Okay, we remove the root and then reheapify the remaining part. That'll again put the maximum minimum element as the root. That'll be removed, and then we reheapify, and then finally we end up with a sorted array. So I talked about this basically, and you can just read on all these if you want. And so this is the entire process basically, that what's happening, right? So we just go through, we compare the children and all, and then we create a binary heap, and then we remove the root. Then after the root is removed, the heap property may be nullified, right? So for example, if you have max heap, then the root is removed, then we might end up with a parent that's smaller than the child. So that's why we should reheapify, and we should ensure that the max heap property is maintained. Each parent is bigger than or equal to its children. So we will reheapify the remaining part, right? After one element is out of the flow, we'll reheapify the remaining part, and then that'll ensure the next element is right at the root, and then that'll be extracted, put right before the other element, and that's how we end up with that. So you can read these if you want yourself, but I prefer to work out with the graphics. So here we go then. So just an example for max heap in ascending order. So this is the array that we are given, 4, 10, 3, 5, 1, right? So we're gonna build a complete binary tree out of this. Okay, we're gonna build a complete binary tree, and then we're gonna heapify it. So this is a complete binary tree. Okay, so it's 4 and its children are 10 and 3. Okay, we talked about this with the array representation of a tree, right? So this is an array. This is how we can represent it as a tree. So this is a 4, and these 10 and 3 are its children, and then these 5 and 1 are childs of 10. You can clearly see, right? We talked about this, the tree representation of array, or we can take an array and represent it as a complete binary tree. So first we make a complete binary tree out of it, and then we heapify the binary tree, right? So we have a complete binary tree, right? And then we go through all the elements and make sure that the parent is bigger than or equal to the root. Sorry, the parent is bigger than or equal to its children. So that's max heapify, right? So as I said, ascending order, you're gonna build a max heap. Descending, min heap. So now we will do max heapify, and we will go through each child and parent, and ensure that the parent is greater than or equal to the child. So we come here. So okay, we got the array, and then we created this tree out of it. So basically this is what we're going to do in code, right? So this is just graphical display, but in code we're just going to code it like that based on these indexes that I said, right? We're going to have this index, the indices that I said, the parent is going to be here, these are going to be his children. So that's how the code will operate, and compare the parent with his children and all, and see if the heap property is maintained. Good, no problem. If it's not, then it's going to swap and all. So it's good to know, the concept, how it's done. And then with code, it's going to be not that difficult, basically. In code, it's just going to be implementation of that algorithm, right? So in here we come. So we should make sure that it's max heapified, right? The max heap property is maintained. Each parent greater than or equal to child. But in here it's nullified, 4 is smaller, so we swap it. 10 goes there. And then it's again nullified. 4 is smaller, so 5 goes there. And then we come here, it's okay, and it's okay. So now it's after max heapifying, this is the final tree, right? Each parent is greater than or equal to its child. And then what we're going to do, we're going to remove 10. After 10 is removed, so that's the final element of the array, right? And then we're going to be left with this tree, which does nullify the property. Look at 10 is removed right to the end of the sorted array. So that's the final element, and then the other elements will join it, and then we're going to have a final sorted array in our hands, right? So after 10 is removed, we can clearly see that the max heap property is nullified, right? It's it's hit and affected by that removal, since 1 is smaller than 5. So we again reheapify. We reheapify the tree, and that'll put 1 in there, 5 in there, and then 1 is also, we said every parent greater than the child, so 1 is going to be smaller, so then again a swapping, and then this is going to be the final tree again after heapify. So this is what we're going to do. So then 5 is the root, we'll put the 5 here and then reheapify. This goes there and all, and then 4 is removed, and then 3 goes there, and then 3 is removed, and then finally 1 is put there and then removed, and then that's it. We end up with a final sorted array. So this is how we sort using the heap sort, right? We create a binary heap, whatever binary heap is needed, basically for ascending order max heap, for descending min heap, whichever one is needed based on the situation, and then we create a binary heap, and then constantly remove the root to the end of the array, and then we create the final sorted array one element at a time, and that's it. That's how we sort an array using heap sort. So this is a video, and I guess we should take a look at it. Okay, so here we go. We have an array we should sort, right? So we will first up, we will make a max heap out of it. We want to sort it in ascending order. So this is what's happening, right? We're creating as we're creating the binary tree, so we can just create the binary tree and then apply the max heap. It's just no problem. So in this video, basically, it's just creating the tree, and while it's creating the tree, it's applying the max heap property. Okay, it's ensuring that each parent is greater than or equal to the child. And after that, as you saw, 12 was the final element, and it was removed, and then 11 removed, right? So I guess you now have enough information to know what's happening in here, right? Here we go then. So that's a problem. 7 is swapped, and then it's when the binary tree is fully created, the heap property is maintained, and we have the biggest element in the root, then we just extract that to the end of this array, to the sorted part, and then again reheapify the remaining part of the array, and then after it's ensured that the heap property is maintained, then the root is removed. Okay, so you can always pause the video and then inspect this animation in more with more detail, with more attention if you want, right? So that's how the array is sorted using max heap, using the heap data structure, right? Okay, then we have min heap and descending order. So basically we talked about max heap, which is used for ascending order, but if you want to sort an array in descending order, so it's just the exact opposite. We create a min heap, right? The example and the animation were all based on max heap, but descending order is just the same thing now. It's just the process and everything is the same, except that we make a min heap. Okay, we take the input array, we make a min heap out of it. We make a heap that has each parent smaller than or equal to its child, right? We create a min heap, and then we repeatedly extract the root, then we reheapify the remaining part of the array to ensure that it's also that it has the min heap property, and then again remove the root element, which will be the smallest, and finally one by one we will create the final array in descending order. So that's it. So in here I have Python implementation, which you can take a look and analyze what's happening, right? So we define a function. We say the largest is it's just again, so as I said, those indices that we said, those formulas for indices and all, what's the parent, the left, right child, those are going to be used in coding here, right? To specify that this is the parent, these are the children, and then go through, see if is the parent, so this max heap, right? Is the parent greater than or equal to the child? If good, no problem. But if it's not, swap them. Then swap this heapify function will create the heap, and then the heap sort function uses that heapify function, right? So this is like a helper method. So in heap sort, we give it an array, it heapifies it, just exactly what we said, right? So that was the explanation of what this code is doing. That was the explanation of the algorithm, and this is what the code is actually doing. That was the explanation of what the code is actually doing and what the code is meant to do in the background, right? So it goes through the array and then heapifies it. Then when it's heapified, it removes, one by one extracting elements, right? It just removes, extracts the root, and then again heapifies. And we know what we do in heapifying, right? And then we go through all the elements until there's no element left, and that'll ensure that it's heapified, and then we'll extract it, heapify and extract it, and then we're gonna be left with a final sorted array. So this is max heap implementation, and this is min heap implementation. So it's just the differences between small and large, right? Only the change comes in there. In max heap, every parent should be greater than or equal to the children, and then in min heap it should be less than or equal to its children. So anyways, basically you can just analyze this code, or we know that we have ChatGPT, we have Copilot at our hand. You can just go there and take the implementation and ask it to explain it for you in detail, and also give you a sample tracing, or you can just take this code and put it in a debugger, and a debugger in an application, and then just analyze even each step one by one as what's happening, right? Step into it and trace it, as we say, right? Dry run, or trace the flow of the operations and with the code, and then you're gonna understand it much better. So I hope heap sort was I hope this was clear to you, and I hope it's clear enough. It was clear enough, and now you know what's heap sort, and we went through the example, the animation, and some general information about sorting algorithms, and I hope it was clear to you, and I hope you've learned something, and thanks a lot. I'm very grateful. So peace out, farewell.